Let's have a look at the solution to this problem here. We've got a roller coaster on a track. We're given some bits of information. So we're told here, look, we've got 35 metres above, which is that dimension there. We start at rest, so that tells me that the initial velocity is 0, and we're lifted to point B. So if we're going from A to B, then presumably at some point later it's released, but that's not part of this first part of the question. So the car and its passengers have a total mass of 550 kilograms, and it takes 25 seconds to lift the car from A to B. It starts at negligible velocity and moves unpowered along the track. Right. Calculate the power used to lift. So we're assuming we know that power is equal to work done over time. We know the time, we don't know the work done. Now if we're lifting something up, we're doing work against gravity, so we're storing gravitational potential energy, and we know that gravitational potential energy is it's mgh, which is 550 times 9.8 times 35 meters, and that gives me an energy of 188,650. That's too many significant figures, but we'll leave it like that for now. Right, now we know the work done, that's in joules. The power is equal to work done over time, which equals 188,650 divided by 25, which equals 7,546 watts. So we'll round that to 7,500 watts, or 7.5 kilowatts. Okay. Next part. The speed reached by the car at C, the bottom of the first dip, is 22 meters per second. The length of the track from B to the bottom is 63 meters. Okay, so we're told then it goes from here to here and reaches a speed of 22 meters per second here. We know that it's got 188,650 joules of energy here, and it loses that as it falls and gains kinetic energy. So presumably, because we're asked to work out resistive forces, if we work out the kinetic energy at this speed, it'll be less than the gravitational potential energy it had here, and the difference is the work done against friction. So there's a number of different stages to this problem. Okay, so if we start by working out the kinetic energy at the bottom, we know that's a half mv squared, so it's a half times 550 times 22 squared, which gives me 133,100 joules. Okay, previously worked out that it had 188,650 joules of energy at the top, so work against friction, in other words the energy transferred because friction's been acting, is 188,650 minus 133,100, which is 55,500 joules, and that's the work done against friction. And we should know that work done is force times distance. We know the distance is 63 meters. We know the work done is 55,500, and therefore we can work out the force is work done over distance, which is equal to 55500 divided by 63 meters, which gives us 881.8 newtons, which is too many significant figures, so I'll do it as 880 newtons. Job done. Right, next part of the question. Oh, no, it's another part there, sorry. Explain why resistive forces are unlikely to remain constant as the car descends from B to C. Right, there's 3 marks, so we need 3 points. Right, firstly, air resistance varies. Secondly, friction will vary. We need to look at why that is in a minute. Okay, so there's 2 marks. Now your third mark is for explaining why one or other of those happens. Well, air resistance varies. Air resistance goes up as speed goes up, so that's easy to explain. But friction will vary because of changing angles. Friction depends on the normal reaction. So here the normal reaction will be this way and be larger because it was balancing a bigger component of the weight, whereas here the normal reaction will be in this direction, and so there'll be less of the component of the weight acting in that direction. So the normal reaction gets less, so friction gets less. Okay. So air resistance varies because air resistance increases as speed increases. Friction will vary because the angle of the track's varying, so the normal reaction will vary. That's a harder one to get the mark for, but you only need to mention one to get the mark. Right, last bit. This is the bit that's on circular motion. So we've got 55 kilograms upwards reaction force of that. When the speed is that, calculate the radius of the track. Okay. It might help if we draw another diagram here. So if we draw the circular bit of the track at the bottom and the car at C, which is at the very bottom of the track there, well, we've got a number of forces acting. We've got the weight mg and we've got the normal reaction there. Now if the car wasn't moving at all, then those two would be equal, but since it is moving and it's going in a circle, then this needs to be bigger than this to provide the resultant force, the centripetal force, towards the centre of the track. So the resultant force is R minus mg, and that's also equal to the centripetal force. So R minus mg is equal to mv squared over r. This r is the radius of the track, and this r is the reaction force. And we're told that the reaction force they experience is 2,160 newtons. And we want r here. So, rearrange. R is going to be equal to mv squared over r minus mg. So 55 times 22 squared. This is just the passenger inside the carriage now, not the carriage as a whole. Well, it's only 55 kilograms. All over 2160 minus 55 times 9.8. Close brackets. Equals 16.4 meters.